we look into Dalton's law of partial pressure. Okay, so in Dalton's law of partial pressure, it states that in a mixture of gases, the total pressure of the mixture is the sum of the pressure of the individual gases, meaning that each gas in the atmosphere, independently of the other, you have a partial pressure, the same pressure it would exert as it were present alone. Meaning that in the atmosphere we have nitrogen gas, we have oxygen gas. So each of these gases has their partial pressure. They have the pressure. So this is the partial pressure in the gas. So this is the gas. So I have nitrogen gas here, which is about 78.09% of the air or dry air. Oxygen is about 20.9 to 20.95, about 21%. And then we have argon and other gases, which is 0.93 and 0.03 respectively. Okay, so as you learned in physics, the total atmospheric pressure at sea level is about 760 millimeter mercury. Okay, so by using this value of total atmospheric pressure, okay, we can determine each types of gas that contribute to the total atmospheric pressure. Okay, meaning we can determine how many pressure is nitrogen giving to the atmosphere, oxygen and other gases. So this fraction is called partial pressure. So the partial pressure for nitrogen, we have this calculation. Oxygen, we have their partial pressures. Each of these gases has their partial pressure. Okay, so thus at sea level, the partial pressure of nitrogen, oxygen, and carbon dioxide are based on this calculation. So partial pressure for nitrogen, 760 millimeter mercury, okay, multiply by 78.09%, you get 593.5 millimeter mercury. So this is a partial pressure exerted by nitrogen. And then we can calculate for oxygen, which will give about 159.2 millimeter mercury. And then for carbon dioxide, which is about 0.2 millimeter mercury. So these are the partial pressure at sea level for individual gases. Okay, so each gases move from the region of higher partial pressure to lower partial pressure that we see in the Fick's law of diffusion. So by having an increase in differences, okay, or increase in partial pressure differences, ensure efficient gas exchange. So this is indicated by delta P in the Fick's law of diffusion. So the bigger the differences in partial pressure differences, okay, the better or the more efficient is the gas exchange. So in human, okay, so this is an example. The partial pressure of oxygen in the alveolus is about 105 millimeter mercury, indicated by the number 2 here. So number 2, so this pressure is about 105 millimeter mercury. Okay, in the alveolar space, we have 105 millimeter mercury, which is lower compared to the atmosphere, which is 159. Okay, indicated by number 1 here. So the differences in the partial pressure cause air from the inhaled air to move into the alveolar space. Okay, so because of this lower in partial pressure. Okay, so next, okay, after that, as blood passes through the capillaries in the rest of the body, the oxygen will leave the blood and diffuse into the tissue. So the blood, okay, so we'll have 105 millimeter mercury passing through into the heart, okay, and then it arrives into the body tissues. So the tissues has lower compared to the blood, which is about 40 millimeter mercury. So this will cause oxygen gases to move from higher, which is 100 millimeter mercury, down to 40 millimeter mercury. So they will pass into the body tissue. Okay, so this is what happens. This is what we see in oxygen transport. So in certain cases, especially among hikers, mountaineers, okay, where they go up into areas with higher altitude, okay, so at higher altitude with 20.95% oxygen, the atmospheric pressure is lower, which is about 380 millimeter mercury. So this is the total atmospheric pressure at higher altitude. Okay, so the partial pressure for oxygen is about 80 millimeter mercury, so which is lower compared to the one in the alveolus, which is about 105 millimeter mercury. So that is why mountaineers, such as those climbing Mount Everest, they require additional oxygen tank. They require oxygen tank to breathe at this low atmosphere. Why? Because the pressure of oxygen is 80 outside. Inside the lung, okay, or the partial pressure in the alveolus is 105. So the inside is higher compared to the outside. Therefore, gases cannot go into the lung because of this low pressure of oxygen.